Hello, Math 133 students. In this video, I'm going to go over the second part of the Chapter 9 flowchart guide, which is regarding sample size. Now, sample size questions, instead of saying construct this confidence interval, what they're going to say is how many or what sample size. You want to beware the word confidence because it's going to appear in these problems, but you want to look at the question words. So you want to look for those question words of how many or what sample size, because they'll say, how many do I need to construct a confidence interval? But they don't actually want you to make the confidence interval. They want to know about how many and what sample size, right? How many people do we need to poll? So just be aware of that. The word confidence appears in these problems, but it's not asking for a confidence interval, as opposed to the ones previously that will actually say, make a confidence interval, build a confidence interval. So instead of saying construct, they might say build, but it's the same idea. Whereas here, they're going to say, how many do I need to build a confidence interval? So it's really how many that matters. All right, now there are three main formulas that we learn in Chapter 9 regarding this. We learn that if we want to work with a proportion that has a prior estimate, it's p hat 1 minus p hat z alpha over 2 over the error squared. I was thinking about my squared error. I found it right here. It's right in your gold sheet on page 300. It's the third box down, but on the left, this one. Okay, so this would be page 300. Oh, sorry, the section we learned this in was 9.4. Technically, it comes out of 9.1, but I pulled it from that section. And it's page 300. It's the third box. Now, what you're going to look for are some keywords. I mean, for one thing, it's going to discuss proportions and percents, right? So you're going to see that somewhere in there. And then it's also going to talk about the past. It's going to have a prior estimate, as in some old survey from the past. Right? Last year we did a survey and it had this much. That's a prior estimate. It's a p hat from the past. So if you see some old value for p hat from the past, this is the one you're going to use. Now you can see you're going to have a critical value of z alpha over 2, which just like for when you're constructing the confidence interval, you find it either with inverse norm, and you'll use alpha over 2 comma 0 comma 1, or you'll use the bottom row of the t-table. All right. Now, what about this one? So this one is for if I have no prior guess. So if you have no prior guess, you would use 0.25 z alpha over 2 over the error squared. This also comes from section 9.4. Again, it actually comes from section 9.1, but I pulled it from there because it made that day so long. So this is page 300. It's also the third box. This one's on the right, as opposed to this one, which was on the left. So let me show you that really quickly. So if you look at page 300, here's the left, here's the right. Right? So this is with prior guess. See the prior? So we have some guess from the past as to what p hat is. And this is when we have no guess what p hat is at all. So what you do when you have no guess of p hat is you put in 0.5 over here. 0.5, 1 minus 0.5 will be 0.5 times 0.5, which is 0.25. This formula actually is this formula. Some books actually only give you the one on the left, but I'm nice and I give you the one on the right also. All right, so this would be also looking for percents and proportions. So let me write proportion. Oh, that did not work out. Proportion. Percent, right? But it'll have no guess for p hat from the past, right? You'll have no clue from some old study or anything what p hat could be. Sorry, my proportion word got weird there. And again, your critical z-values are z alpha over 2, c above, right? We don't need to go over how to find them again. It's the same as above. Next. Okay, so these two are very similar. They're talking about proportions of percents. It's just a question of, do I have an old guess or don't I? But what if it's something else entirely? There's only one that works like this. And I wrote it differently in the notes as opposed to in this. And they both work, but realize there's a multiplication in there. So it's z alpha over 2 times s over error squared. This is the one, it's the only one actually that will ever involve means. It'll have a standard deviation in the problem because there's S, and S is the standard deviation. It'll talk about average, right? Just like before, average becomes a word for mean, even though we in the stats class know that's technically not accurate. There are lots of averages, for example, the median, the mode. But in these later problems, the mean is our only option. So if they talk about average, then they're talking about the mean. Now, this was also section 9.4. Technically, it was actually section 9.2, but I pulled it out of that. And it'd be page 300, and it's the fourth box. It's the last one on the page. Right, it's at the very bottom. So first two boxes are confidence intervals. Second two boxes right here, it's the last one right there at the bottom. So 1 box, 2 box, 3, 4. Here it is. Or if you like, it's the fifth one of the things I circled. All right, and the critical values again are z alpha over 2, c above, as regards to how to find those, right? Inverse norm or the bottom row of the t-table. Now, there's some tricky bits to these three formulas because they don't work like other things that we've had. For one thing, you must always round up, no matter what. Always. Even if your answer comes out to like 260.02, you round up to 261. You never let a 0.0 decimal sit out there. No decimals of any kind. So you must always round up to the nearest number. But it's a different kind of rounding than we are used to. 99.9% of the time in a math class, you regular round. 5 and higher goes up, 4 and lower goes down, but not in this case. This is one case where we must go up. In proportion problems, change the given percentage error into a decimal. So a lot of times they're going to say within, let me just give you an example. They'll say within 3%. You turn that into 0.03. You don't leave it as a 3. You make the 3% turn into a decimal. You must. If you leave it at 3, you will be crazy wrong. If you end up with an answer that's like, I need 2 people, that's a sign that that's what you did, by the way. So always double check. You should be getting some numbers here. You shouldn't get like, I need 4 people. So if you get 4 people, that's a sign you did this wrong. I need less than a person, you did this wrong. This is a really common mistake, but it's only true for these two. It's only true for the proportion ones, not for the mean one. The mean one's kind of its own thing. Right? So for this one and this one, you have to worry about that decimal, this bit right here. One other thing real quick, with the one down here, you don't have to worry about it because the mean doesn't have those same properties. You're doing it for these two because we frankly write the percentage, the error as a percentage, and so you just have to change that to a decimal to make the formula work. Right? And another key word, I guess I didn't write it in here, is error is often like given to you with the keyword is within. I want to be within this many. I want to be within 3%. I want to be within $1,000. Right? So that's a keyword that'll kind of in the problem you'll be able to spot your error for that way. All right, and just as before, just we did in the previous problems, there's relationships between error and sample size. So notice, look at where error is in all three of these formulas. The denominator, right? So if the error goes up, then the sample size goes down, right? It's the twin to what we did on the previous page, right? When sample size goes up, error goes down, and vice versa. So we just saw that. It's here too. right? You can reverse it. If error goes up, n goes down. If error goes down, n goes up, right? There's a relationship there. It's literally the same relationship as the previous page. Confidence. Well, the confidence going up would make this z-score go up, or this z-score go up, and those, or this one. And those z-scores are in the numerator. So if they get larger, then the error gets larger. So if your sea level increases, then the whole thing, because it's in the numerator, if that goes up and makes it be it's a bigger number, then this whole thing is a bigger number, which means n is a bigger number. So if your sea level goes up, then n will go up. And by the same token, if sea level goes down, n will go down. And it makes a certain kind of sense. If you want to be more confident, go sample more people. Like if you want to be 99% sure, go get 2,000 people. You'll be sure, right? You won't be 100% sure because you can't be, but you'll be more certain. Okay? Standard deviation only affects this green one right here. Standard deviation is that S right there. Now notice it is also in the numerator. So if it gets larger, then this whole fraction gets larger. And if the whole fraction gets larger, then n gets larger. So if S goes up, n goes up also. And then just another note, what I just said, but I thought, oh, I should put that down. So note, the sea level can never be 100%. As in chapter 10, we learn there's always room for error. There's always a possibility of doing false positives, false negatives. So we're never going to be 100% certain. And that's true here. So you're never going to be able to make an n large enough to be 100%. So you can just make your n get larger and larger, so you're more and more certain, but you'll never be 100% certain. There's always a possibility for error.